It's very nice to be here. It's really a place where I can learn a lot of things in a broad direction. So from mathematics, there will be a lot of mathematics here, for example, to very applied topics. So it's a very nice conference, and I'm very happy to be part of this. So my goal today is to explain you a bit what is this signature. It's an object that is very beautiful for mathematicians. We like it. But what is more important is also useful, okay, because it's tractable and understandable. And if you use it, you can simplify many other things and do things that maybe you thought that they were too difficult to do. So why do we like signature? Well, there are two main reasons. The first one is because the time-extended signature of a continuous remarking and uniquely determined path. Okay, very cryptic sentence, but the meaning is that maybe instead of using the whole trajectory of the object that you're interested in, you can use its signature. Okay, so looking at the signature at a given time t, you have all the information that is contained in the trajectory. Okay.
Why continuous semi-martingale and not semi-martingale?
You can also do with Calibration. The signature get a bit more complicated.
Yes.
Yeah, but you can do it.
You can do it.
Because every polynomial in the signature has a linear representative. Every time that you write a polynomial map, you can also write as a linear one. We will see an example, and then you see immediately where this link comes from. If you combine these two properties, you get something very useful, because imagine that you have a quantity that depends on the whole trajectory in a continuous way. Then what can you do? You can go from the trajectory to the signature. Okay, because all the information are contained there. And then continuous map can be approximated by polynomial ones, based on Weierstrass. Polynomials can be written as linear maps. And so you go from something like this, that you can imagine is quite complicated and difficult to handle, to a linear map of the signature. Okay? Here you can resource to things related to linear maps that you could not do here. Okay, so it's not that it's magic, it's just that let you see the same problem in a slightly different way and let you connect with tools that you already had before, and now you can apply it, essentially. Okay, so yeah, you can do many things. Let's understand a bit, just through an example, what would be this signature. If you take the signature of time, what would it be? Is nothing else than the Taylor basis, okay? And you say, you can already see some properties. So if you multiply two of them, you get another one, okay? So you go from a quadratic map to a linear one, for example, okay? You say, okay, till here, nothing so interesting. If you move to a continuous semi-martingale, exactly the same. The Taylor basis in the semi-martingale. Again, you see this property. Now, if you multiply two, you get another one. And then you say, okay, but you say that you get information about the trajectory from 0 to t. True.
But this doesn't require continuous.
No. This not. Here, if you go in two dimension, you can see that on top of the Taylor basis, there are also some integrals here of one component with respect to the other one. So the first component with respect to the second, and the second with respect to the first. With jumps, you need to be careful on the notion of integration that you use here. If you want the algebraic property that if you multiply two, you get a linear combination, you need to use Marcus integration, which is not even an integration, is more a concept for solution of SDs with jumps. This is why it gets more complicated. Okay. And you know that if you multiply two integrals, you can compute dynamics again, using Ito formula, essentially. And you recover another expression, which is again of the form of iterated integrals, right? And so you recover the same trick that you do with the Taylor, but also with integrals. And you see that in this type of term, you need to know, so you have some information about the whole trajectory, x hat, from time 0 to time t. Okay. Now, let's be a bit more rigorous, okay? So What is the signature? Is the collection of all the iterated integral. It means that you start with 1, then you integrate with respect to x, then you take the object x come out and you integrate again with respect to x, and so on. How many times as you want. Okay? Integration are Riemann stiltes, so now we are working in finite variation such that we do not need to care about which type of integral we want to use. Okay, now we first understand this such that then with semi-martingales it will be a bit easier. Where does this process live? In the tensor algebra. The tensor algebra is like a sequence space. So you save a spot for each of these integrals. There is a spot for the one, a spot for the single integral, a spot for the second integral, and so on.
I can do all this in discrete time.
In discrete time, yes.
Yeah.
Sure. You can do it.
So you have the discrete time integral.
Exactly.
Of the signatures in the
Yes.
discrete time model.
In discrete time, you can do it both with the step functions or with the linearly interpolated points.
Right.
Yeah.
Okay.
We need then a notation in order to say I want to take the kth iterated integral, okay? So how do? We said, okay, when we use the empty set, we mean the first one. So nobody's integrated, empty set. And then with this type of notation, we said, okay, if we put 1, 1, 1 3 times and we pair it with the signature, we mean the triple integral, essentially. Okay? Or this or this. So what we put on the left is just to let us know which integral we want to choose. If here there are k times 1, we are integrated k times the one and only component of x. Okay? Note that each integral can be defined as an integral. So each element of the signature can be defined as the integral of the preceding one. So if we already integrated k time and we want the k plus 1 component, we just integrate another time. Okay? Okay. We need to be careful just with one thing. True, we characterize the trajectory up to shifts. So since here we are always taking the differential of x, if we take a trajectory and then we shift constantly up or down, we lose that information. So we always need to take track of where the process started in addition to the signature. Okay, just to keep in mind. Like Brownian motion for plus 3 will have exactly the same signature. Okay, so if we want to summarize, the signature is a collection of elements like that. So one single integral, double integral, triple integral, where each of them is defined as the preceding one integrated another time. Okay. Now we do the same, but with d-dimension. It gets a bit more complicated. Not really in practice, but more on the notation point of view. The notation is very heavy for this type of thing. The space. The space is a bit more tricky because now we have the one means alone, but at level 1 we have d of them. At level 2 we have d squared, okay, and so on. And so we need to save a spot for each of them. And the space is not flat anymore, but we have single, and then vector, and then matrix, and then cube, and so on. Okay, this space that you can imagine that contains a spot for each of them is the extended tensor algebra. Okay, you need tensors in order to get vector, matrix, cube, and then hypercube, and so on, which looks more complicated than what it is, because at the end it's just one spot for each integral, okay? But you need some formality. Then, we need to access component. Now we have many different components of x. So we need to take in account who we integrate with respect to who. So maybe the first component with respect to the second, or the second with respect to the first, and they are two different objects. And so what we do is just we take a vector I, with this I1 with till In, when we say, okay, this means that we take the component I1, we integrate it with respect to the component I2, with respect to the component I3, and so on. Okay, so what we have on the left, just tell us who you are integrating with respect to who. For example, suppose that you have a two-dimensional process y and z. You take the component 1, 2 of the signature. So what do you get? 1 integrated with respect to the first component, which is y, integrated with respect to the second component, which is z. Okay? The first integral can be computed, so this ys minus y0. You see that the constant disappears in y, and you get what is the second component of the signature. Okay. Again, we can define each component of the signature as another component of the signature integrated. So if we want the element of the signature corresponding to 1, 2, 3, we can take the element of the signature corresponding to 1, 2, and then integrate with respect to the third component. Can always be defined recursively, okay? So if we write it in a more compact way, we have a collection of terms like this, where the first one is always equal to 1, is constant, and everybody else is. You take the first indices without the last one, and you integrate with respect to the last one, okay?
So the constants disappear and the scale just scales.
The scale depends on the level. So if you are in triple integrals, the scale comes out with a power 3. Because you are integrating 3 times,
Right.
so you get 3 constant that comes out. Okay. Level 1 is single, and level 2 is double, and so on.
Right.
Exactly, again, like the Taylor basis, which is important, no? Because if you want to do an expansion, it's important that if you multiply by a constant, this goes to 0 quicker and quicker if you go up with the basis. And this does the same also here. Okay, but till now we were on final variation, so Riemann-Stieltjes, the integral was okay. Now we want to use continuous martingale, and well, the definition is exactly the same, 1-to-1 what we did till now. The only bit more delicate point is what do we want to use as an integration here. And we will use 2 things. We can use eta, or we can use Stratonovich. Why somebody would want to use Stratonovich? Well, because Stratonovich is a first order calculus, which means that you have integration by parts. X times y is equal to the integral of x with respect to y plus the integral of y with respect to x. Very nice. No quadratic variation correction, which is annoying because the quadratic variation is not necessarily part of the signature, but the other two, yes. Okay? So when you work with the signature, Stratonovich is nicer than Ito. But Ito is nice because of the martingale property, so it can be interesting to work with both. In here, no problems with any of them. Okay. Now that you know a bit on the signature, we move to the shuffle property. Andrea already mentioned the shuffle property, and this again something that looks more difficult than what it is. We know that both Stratonovich and Riemann-Stieltjes satisfy the integration by part formula. Okay, what I just said 1 second ago. So, what does it mean? Each polynomial in the signature has a linear representation because we can always do something like that. What we have here on the left is the product of 2 level 1 elements of the signature, for example. Okay? Imagine that processes start with 0. What we have on the right is a linear combination of the signature. Okay? Because the integral, and this integral are both components of the signature. So we go for a polynomial, from a polynomial to a linear number. Okay?
But otherwise we carry the covariation term on the way.
Exactly. And then you need to care to manage that. If you are speaking about Verona motion, then it's sufficient that you include also time in the signature, and
Right.
it's okay.
Okay.
But if you speak about general processes, then you need to include also the quadratic variation
All the course.
in the process, and then again you can work with it. But with Stratonovich it's cleaner, no? The algebra is nice. And the shuffle, so there is an explicit map that takes the index I and the index j and tells you how you shuffle it, and you can implement it.
So this is how you're defining the components. The answer is the same.
Yeah.
Okay.
It's nice because it's automatic, no? You don't need to do the Ito formula and then see what comes out.
Right.
You can work directly on the indices and you see exactly what is the linear combination that you need to take.
Yeah.
Okay.
But in the Chaturnivish, the covariation is already gone in there.
Yeah.
Yeah. Okay.
What is more complicated then, so there is always a complication coming out. If you want to compute expectation
Right.
of iterated Stratonovich integrals, this is more complicated because you cannot use martingale to get rid of all of it.
Yeah. Okay.
But if you use it, the product is more complicated, but as soon as you have done the product, then the expectation is much easier. So it's
okay.
Depending on your application and also a bit on your audience. Because there are people that like more, like in rough pass, they like more Stratonovich. In econometrics, they like Morito. So it depends with who you would like to speak. You should choose one or the other one, which is true, I think.
Right.
For example, if you take the component 1 and you multiply with the component 2, you get x1, x2, right? Apply the integration by part formula, you get the first with respect to the second and the second with respect to the first, which is nothing else than the component 1, 2 plus the component 2, 1. So the shuffle of 1 with 2 is nothing else than 1, 2 plus 2, 1. Okay? It's called shuffle because it's like if you take 2 decks of cards and then you mix them. So you cannot mix between the 2 decks, but you can mix between them and you sum over all possible solution. Here you have a deck with card 1 and a deck with card 2, and you want to mix. So there are just 2 combinations, 1, 2 or 2, 1. Okay. Okay. Then,
so when you go higher up, you keep shuffling.
Keep shuffling. Yes, exactly. And it's a bilinear operation. So with the computer, it's saving essentially a cube. So it's saving that. You can do this operation very quickly. Quasi-shuffle property or integration by part formula, if we want to work with Ito, you need to include the quadratic variation. Because Ito formula, you get the quadratic variation. So if you are working with Brownian motion, you include time, and then you are okay, fine. You need to define the product slightly different to take care about the t, but then you can still do the same computation as before. You multiply 2 of them. You get now Ito formula with the quadratic variation, but now t is one of the components of your original process. Component 0, typically. You give a special number to it. And so you get 1, 2, 2, 1 plus rho new component. And again, you can go from a polynomial to a linear map. Okay, so also with Ito, you need to work a bit harder, but you can find a product that satisfies what you want. Okay, so the star product, this quasi-shuffle, is given by this, in this case, combination. Okay, now, this is the signature, a bit from a theoretical level. I want to show you today how we use for doing expansions. There are plenty of expansion in rough path using signatures and using like sophisticated, let's say, you want to apply to have a sort of Ito formula, a sort of Taylor formula, but for functions that depend on the whole trajectory. Okay, it's complicated because you need to understand which space you use for the trajectory, in which sense you want to differentiate them. So there are different ways to do it. We wanted to do it in a way that is sufficiently simple and applicable, okay, in order to have, like without resourcing to all these spaces, just to try to see if we can make our life easier. Okay, this was the goal of this paper. Federico Bandi is in the Johns Hopkins and Roberto Renaud is in ESSEC in Paris. Okay, so let's take an example. Okay, you take a first component of a Brownian motion, W1. I mean first component because later on there will be a d-dimensional Brownian motion, but in this example it's just one dimension. Then you take a process that can be your price, okay? And you imagine that this is an Ito process, so it can be written as something dt, something the Brownian motion. Okay. And then you say, now, maybe C0 and C1 are again Ito process. And so it can be written as something ds, something dw. Okay. Then, what can we do? We can replace, so this C0t in the integral above, and this C1t in the integral above, okay? And then we order terms. And what do we get? Well, a 0 is there and stay there, okay? Then we get C0, 0. So the initial value of this C0 here is integrated with respect to time, okay? So C0, 0 multiplied by time. Similarly, C1, 0 multiplied by Brownian motion, and then there is everything else. Everything else are linear combination of double integrals, okay? If we have a look at what we have here, we have a linear combination of the signature of level 1 plus double integrals, okay? Signature of what? Of Brownian motion and time. So we can do it again. We say, okay, this we already did. This we already did, and we have the double integrals. Now, suppose that each of them are again Ito processes. So each of them can be written as the integral of something dt, something the Brownian motion. Okay. Then we do the same. We replace and we order terms. And what we get is, okay, this was the part that was already there before, plus C0, 0, 0. So again, the initial condition of this that was inside the double integral with respect to time. So we get C0, 0, 0, double integral with respect to time. Then we get the initial condition of this 1, 0 here is integrating with respect to Brownian motion and then time and Brownian motion and double Brownian motion. So we get all the double integrals. And what remains are triple integrals, okay? And you can continue like that. Because what is the idea? The idea is that every time that you integrate, you will go to 0 quicker, right? Every integral with respect of a Brownian motion gives you a square root of t, quicker going to 0. And so if you want to have like asymptotic for small times for t to the n divided by 2, it's sufficient that the error term contains integral iterated integrals of depth n plus 1, and it will be an error. So it will not count for your approximation, okay? Okay, this will be called epsilon 2. So the error that remains after that we subtract all the double integrals. So if we continue in this way, what do we get? We will get a 0. Then linear combination of iterated integrals from depth 1 till depth n. And then linear combination of n plus 1 iterated integrals. And this will be our epsilon n. And there are 3 nice facts about that. First of all, epsilon n is an error term in many cases of interest. Because if it's an you can call it epsilon, but if it's not an error, you don't go anywhere. What does it mean? If you take the expectation of, so if the function that is inside all the integrals is sufficiently nice, like integrable, for example, then the expectation of your error will go to 0 quicker and quicker. Okay, for example. Second observation, if you ignore the error term, so if you look just at the first line, you have a Markov process. So we started from a super general Ito process, and now we land in a Markov process. So you can use Etir-Kurz, essentially. So like all the huge books with all the results about Markov processes can be used now, as soon as you get rid of the error, okay? Even more, the red integrals are signature, which means that they are not just a Markov process. It's an object made by Brownian motion and time, so which are processes that we know very well. We know how to work with Brownian motion, right? And you have nice properties, like the one that you multiply 2 of them, you get another one, and so on. So it's very tractable, this object that you get as soon as the error is away.
So you're saying that we can build a Markovian approximation to an arbitrary process using the Z?
Not arbitrary, because you need to be able to have that every function inside should be again an Ito process. So there is a concept of differentiability, like, okay?
Yeah, but if I do this all in discrete time, I will get a Markovian process.
Yes.
When I truncate at some level.
Yes,
right?
for a small time.
For small time. Ah, because you think the epsilon is getting too big.
Exactly. So yeah, you need to decide. No? It's
Ah.
a bit like Taylor. You can, with a polynomial, you can approximate.
Right. Okay. All right.
So with a polynomial, you can approximate a continuous map using Taylor for small times, or you can approximate a continuous function on a compact, so not small time, but then you need to use like Weierstrass, okay? So it depends. If you want to go with Taylor, with explicit coefficient, you know exactly how to choose the polynomial that approximates the map, or if you want to say...
compact.
Yeah.
Domain. Exactly. Well, they're both reasonable. That's reasonable. Yeah.
Very good. Okay, let's go a bit deeper in these points. Yeah, the first one. Okay, so we have, we said that our process, now we will write it in a more compact way like this. So in the C, is a vector where we put all the coefficients, so all the Ci0, okay? The error term is linear combination of n plus 1 iterated integrals. And yeah, you can prove that, and it's actually not so difficult, that the expectation of this error term to the power m goes to 0 quicker, both in m and in n. Why? So you can imagine to take the expectation of this and then with a square, and you can use either isometry or Jensen. And every time that you go in one more step, you gain some dt. Okay. And so at the end, when you went inside all of them, you need to integrate n plus 1 time with respect to t, and you get this bound here. Okay. This is very nice, because now what can we do? We apply a Taylor to f, for example. So to a function f that we want to, of which we want to compute the expectation. Not Taylor too high, just Taylor first level. Now we said the first derivative is bounded of this function f, and then we can say, okay, then we get f in the point around which we want to do Taylor, which is our linear combination, plus the difference between the original process and the new one, which is the epsilon n. And this will be an error. So every time that we want to compute the expectation of f of s, we can, for t small, we can compute the expectation of the linear combination of the signature. And also moments. So it's, you have a trade-off between the regularity of f and the integrability of the error term. Okay, so there are many things where you can do it. The red term is the expectation of a map applied to the signature process. And the signature process is a Markov process. Okay, let's understand it. We say that each component of the signature is given by another component of the signature integrated with respect to the process. But here the process is either Brownian motion or time, right? So we have another component of the signature integrated with respect to time, drift, pure drift, or another component of the signature integrated with respect to Brownian motion, pure diffusion. So they are always of this form, which is, by definition, so if you look at it, you see that this is a dynamic of a Markov process. And, so, exactly. This is very nice. Why? Markovianity is extremely useful if you want, for example, to expand expectation. Why? Take a Markov process, like a general one, something like that. Then, if you apply the Ito formula, you get something dt plus martingale, where this something is given by this. So the drift, first derivative, plus 1/2, second derivative, quadratic variation. It's just Ito formula, okay? And so what happened? We can compute the expectation of this formula here, the left and the right. We get that, yeah, here I skip a step that would have been useful. If you compute the expectation on the left and on the right, the martingale disappears. It's a martingale that starts in 0. And so you get that the expectation of f of t is equal to the integral from 0 to t of the expectation of what is inside the integral. Which means that if we want to differentiate the expectation, we just need to get rid of the integral and we get what is this derivative. Okay? And we can do it again and again. Every time that we want to differentiate expectation, we just apply G to F. Again, and again, and again, and as many times as you want. And why would you like to differentiate expectation? Because then you can apply Taylor directly to the expectation. And you get something like this. If you evaluate this for a small t equal to 0, it is deterministic, so you get rid of the expectation, and it's just GGG of y0. Okay? And so you get the expansion of f of any order just by applying G recursively as many times as you need. This is why Markov processes are nice. Now we want to use it for our signature, which is the Markov process that we use to approximate the original one. So we are in this setting, we have linear combination of the signature plus iterated integrals. Okay. We say that if f is sufficiently nice, we get rid of the error term, and W is a diffusion. So the only thing that we need to do is to understand what is the generator. So this operator coming from the Ito formula of the signature, and then we apply the formula as it was before. Okay. Evaluated in the signature at time 0, which is nothing else than 1 and then 0, 0, 0, 0, because the integral from 0 to 0 is 0. Okay? Okay. This leads us to the last part, because you said, okay, well, and then you still have G, right? This can be complicated. So we need to now exploit the fact that we are not speaking about Markov process. We are speaking about the signature. Okay? So the generator should be nice. It's linear at the end, the dynamics, no? Okay. So we have that we need to write down the dynamics of the signature to then apply the Ito formula and understand what is the generator. We can see that, we saw before, actually, because I did not report it here, that B and sigma are linear maps. Because what are B and sigma? It's just the previous component of the signature that we are now integrating either with respect to time or to Brownian motion. So, this means that if we take a linear combination of the signature, we get again something which has linear drift and diffusion coefficient in the signature. Okay? Which means that since they are linear, we can write it as a scalar product. There will be some coefficients that depend on C for each component of the signature that we need to go and select. Okay. Next step, we said, okay, fine. This means that if we now apply the Ito formula, we get first derivative drift plus 1/2 second derivative quadratic variation. And so you can see that this is the drift, and this is the diffusion. So the quadratic variation, we will just need to square it. Okay. One more step. Okay. If we now want to take the pairing between, so the signature at time 0, if you remember, was just 1 and then 0, 0, 0. So when we take this pairing, what we are doing is in fact selecting the very first component of C, because the coefficient of everything else will be equal to 0. And so we just need to evaluate the derivative in C0. Okay. Okay, and so, given that our ST can be written as iterated integrals plus error, and since the constant term will always correspond to S0, we get that if we apply this formula directly, we get f of x0 plus this expression that we just computed here, which is extremely simple to compute. Okay? So first derivative in S0, we take the coefficient of C and look at the very first component, and similar here. There is also that I did not mention here, the square. Okay? Here we are doing exactly the magic that we described before. that you can go from a polynomial of degree 2 to a linear map through the star, because here we are using Ito integrals and not Stratonovich, so we need to use the quasi-Shapiro thing. And so you get your expansion. You just need to implement in your computer what is this linear operator B and this linear operator sigma, and you can do it very quickly. You can also do it, so putting pieces together. If you want to write your expansion, you can start with saying, okay, I have a process which is iterative integral of time and Brownian motion. How many Brownian motion you want? Plus an error term. You get rid of the error term using Taylor and you stay with your linear combination of the signature. You use the fact that this is a diffusion to expand the expectation using Taylor. And finally, you use the fact that since W is a signature, you can compute this operator by means of some linear maps. And so you get your expectation. Now, let me see, to calibrate a bit. I still have around 15 minutes?
Yeah.
Okay.
20.
20. Very good. You want to do it again, okay? Now it's a little bit more complicated because you need to look for similarities between what you get, your original function, and what you get after applying the generator, okay? So you can observe that if you compute the generator, if you look at what is the generator of f of your linear combination, you get something of this form. Okay, this is what we already saw before. And you can see that this has a very specific structure that is given by some derivative of f in the original linear combination times some linear combination of the signature. Okay? And this happens again if you apply the generator to functions times linear combination of the signature. You can see that if you do it, you get again something of the form derivatives times linear map of the signature. Okay? So, since we want to do it again and again, we want to do it in an automatic way, we can work with this type of thing here. Because then we just need to understand what are the three operators, G0, G1, and G2, in order to understand, to be able to repeat this procedure as many times as we want. Because now each of these three terms are exactly of the form to which we apply the generator. So we can apply the generator again just by repeating the same formula. G is mapping functions of the form function to the original linear combination times a new linear combination to something of the form some derivatives times linear combination. And so you just need to understand these three operators, which are linear, so they are matrix in particular, to be able to automatically apply it as many times as you want. This leads to then the theorem, which is of this form here. I know that maybe at first look it can seem complicated, but actually is extremely explicit. You can expand the expectation of f of your original process S, which was just an Ito process, whose coefficient was again Ito processes, at the order that you want by applying recursively these linear operators G. Okay? So this can be done by a computer, because multiplying by matrix is something that the computer are very good in doing. Okay, an example. So suppose that S is of this form, and we expand till order 2, and then we have the error. Then, if we apply the theorem for n equal to 2 to the characteristic function, not normalized, just characteristic function, you get exactly this expression here. Okay? So, if you want, you can also go deeper, doing other orders. You will need to understand also what are the other coefficients, so like to go deeper in the expansion with the signature, because you will need to know also other coefficients, and you get your expansion. Okay. Now, we also did this with the jumps, and here we do not use Marcus, because we wanted to stick with it. But it's still a bit more annoying because the good news is that error will go to 0 in end. Okay? So if you iterate integration with respect to a Poisson process, it will go to 0 quicker and quicker. But this implies that you can still split and recover your Markovianity. But you lose the nice algebraic property, because when you take the square of a Poisson process standard, okay, no problem, but of a general Levy process, for example, you, in the Ito formula, you also get the term which is given by the sum of the jump squared. And this cannot be written as a linear combination of iterated integral. It's a different process, okay? So you will need to include that too in your original process. But then, of course, you will also need to have the power 3, the power 4, and 3, and so on. Which is, yeah, a bit annoying because the notation gets heavier, no? In a sense. And, yeah, well, still, you can do it because you can say, okay, if I want an expansion of order k, then I include power still order k. I will not have the nice algebraic property for every order, but at the end, if I want to reach level k, I will need higher order, no? And this is what you do. So your notation gets a bit more crazy, and you get that on the positive components, you get the components of the Brownian motion, and on the negative one, you get the power of, in this case, the single jump component. You can also have more than one jump driver, but then the notation gets even more involved. Then the product of the time extended signature, okay, can be done. And here you resource to your component of Z corresponding to the square jumps. Then, now this is, okay, I will not enter to detail on that, but the point is that finally you still get an expansion. It's more complicated because when you apply the Ito formula to jumps, you also have an integral there, so not just derivatives. And so you need to be a bit more, to consider some more operators and also to have some integrals. So depending on the distribution of your jumps, you get different integrals that you cannot get rid of a priori. Okay. You can generalize to power, so polynomials so if you want to compute moments of your original process, you can consider a d-dimensional Brownian motion, correlated or not correlated. You can consider also E different compound Poisson processes. Or also, which is important to say, here we were doing the expansion, okay? But we are speaking about a Brownian motion. So we know a lot of things about Brownian motion or two Levy processes, okay? So there are also many other things that if one can do if you have linear combination of the signature and you could not do before when you had the general process. One can do, for example, the Edgeworth type of expansions, which are not a direct application of what I show you because there is this annoying division by the square root of t, which makes the function itself not differentiable in 0. Okay? But still, so you need to work a bit in order to understand how to cast this case using the property of the Brownian motion, but then you get. So the mathematics that I'm showing you is not that there is something incredibly new. Okay? At the end, we use Ito formula, we use Taylor, and we use expansion for Markov processes. The point is just that if you put them together, you can do this type of expansion, but without applying Ito by hand and then checking every single process that comes out and understand why this is an error term and why you can get rid of it. Is everything can be done in an ordered and consistent way. Okay? Okay. Then, just to give you a very overview of the more like Stone-Weierstrass approach. Now we saw Taylor approach, so small times, but you can also say, no, I'm more interested in a Stone-Weierstrass type of approach. I give you some illustration of what we did with Christa Cucchiero and Guido Gazzani. This was my first paper on the with the signatures. And yeah, I think that is good to have also this other type of view. I told you at the very beginning that knowing the signature at time capital T, you also have the information about the whole trajectory. Okay? This is actually easy to prove, again, because you know that knowing the signature, you know this type of quantity. Why? Xi minus X0 is a component of the signature. S is a component of the signature. Here we are considering the signature of X and time together. Okay? So S is an element and X is an element. Polynomials of them are again elements of the linear combination of the signature, right? And as soon as we have linear combination of the signature, if we integrate with respect to one of the component, we get again linear combination of the signature. So this type of integral here can be written as a linear combination of the signature, which means that knowing the signature, you also know all the value of all these integrals. And now you just need to use the fact that polynomials in time are dense on 0t, okay, on the compact set, which means that with polynomials, with this sk, you can approximate a bump function, no? And if you approximate a small bump function on 0t, you can let this integral concentrate around a single point of x. And so knowing this for every k will let you also identify exactly what is the value of x in every point. So knowing the signature, you also know x in every point between 0 and t. This is very nice because you can recover Markovianity. Because if before you wanted to work with the whole trajectory, now you can work with the signature at time t. And you don't need to care of what happened before. Okay, so now what is the idea? The idea is, okay, then if we take the signature of level 2, we can say if we consider whatever function which is continuous on the signature of level 2, it can be approximated by linear combination of the signature. Okay, why? Because you go from the trajectory to the final point, from continuous function to polynomials, from polynomials to linear maps. Not that here I'm being on purpose a bit sloppy on what do we mean by continuous, because if you want to define what is continuous, you need a topology on the space of trajectory, and also to what do we mean by compact set. But still, this is the principle, okay? And there are many interesting functions like that. For example, strong solution of SDE can be written as a continuous map of the driver of the Brownian motion. So if you take a strong solution of an SDE in a given point, it can be approximated by a signature of its Brownian motion. Okay, time extended Brownian motion. Okay, so this show, or like give an intuition about the fact that modeling using linear combination of the signature is extremely flexible. Okay, because you can recover each strong solution of an SDE. So the model that we consider, I will be a bit quick, is saying, okay, we take the price and we take it to be a linear combination of the signature. Of what? Of whatever you would like to use. It should be an object that you know and that contains the randomicity of, for example, the price that you want to use, like a Brownian motion, for example. And then, so if you want, then as soon as you have it, of the deep that you would like to have, then you can try to see if we can fit, for example, implied volatilities. And we can, so what we saw is that it's really possible to get it and to reproduce quite well the implied volatility that you see on the market. In this case, we went to level 3, so till triple integrals. We did not take in account for integrals, and we also impose martingality on the price, because here we are modeling under Q, and so to be sure that there are no arbitrage, we also impose the last integral to be in Ito sense and not in Stratonovich one. Okay. Also, if you want, you can also model you can also manage to fit both the VIX and the S&P implied volatility. Because what is nice is that, where is it? Here. If you choose your primary, so the object of which you compute the signature in a reasonable way, a polynomial process, so which means that it includes like OU process, CIR process, Brownian motion, this type of processes here. If you use them, then you can compute the expected signature in closed form with a matrix exponential. And this is important because the VIX can be computed using this formula. So if your sigma square is a linear combination of the signature, that conditional expectation can be computed explicitly. And you can get the dynamics of the VIX without any simulation of the conditional expectation that we all know is quite painful, okay? As soon as you get explicit dynamics of both the price and the VIX, then you can calibrate also using Monte Carlo if you want. In particular, because the model is a linear combination of the signature, which means that if you want to update your parameters, you don't need to simulate everything by the beginning. You can have your trajectory saved somewhere, you do the scalar product and you get the new one, okay? So it's very quick, and for this reason you manage to calibrate it. So even more, and this I think is my last slide, you can include jump. You can say, okay, but now we are always working with truncated signature. But maybe it's nice to also consider the whole signature. Like, for example, if when you work with the Taylor basis, no, you can work with polynomials, but you can say, why? We can also take the whole series and work with Fourier basis, no? So maybe polynomials is not the best way to work with a Taylor basis. Maybe there are other ones nicer depending on the applications. For example, we are speaking about power series. So maybe we can also use results from complex analysis to understand when a transformation of a map, of an entire map is again entire. This works well with derivatives, with multiplication. With integrals is a bit more painful because understanding when the integral of an entire map is entire is not so direct, but you can do it. And there they have very powerful results that's very nice to apply. One can use duality theory, which means that duality theory is when you have two processes that, for which if you have a function that depends on both of them, they share expectation, meaning that you fix one and you let the second one run, you get exactly the same expectation than fixing the second and letting the first one run. And this lets you get tractable representation of expectations. One can, and this is what showed you Andrea yesterday, not limiting yourself to the VIX, but also going to the VXX, so like vol of vol type of implied volatilities. One can consider other algebras instead of the polynomials, what I just said. You can consider Fourier if you like Fourier, or also other ones. And yeah, so those are the things that I managed to consider in the last times, but actually there are plenty of people that are working now with the signature in many different ways, for control, for example, also. And yeah, and I hope that I convinced that now we should all start to work with signatures. So thank you very much for your attention.
Questions?
So, if I have an additive process,
Yes.
and I know the Levy structure,
Yeah.
and I understand that I can break it into small t's.
Yeah.
And for each small t, I work out a signature
Yeah.
for that movement. And I work out Markovian approximation.
Yes.
So this way, I can build a finite state Markovian model. And I would then like to be able to compute the characteristic function of that Markovian system. Is that accessible?
So there is some work then one need to do for that. Exactly like not every real analytic function is also entire. For doing what you are saying is that you need to be careful in how you can glue pieces together. Okay.
Right.
Yeah. And there are some work that has been done also, like in the 80s, but it's something that, to be honest, I'm still studying to understand exactly how you can do what you just said.
I see. Okay.
Okay.
Other questions? We are still digesting signatures.
It's okay, it's okay. It's fully understandable.
I myself have a statistical, basic statistical knowledge of signatures in the space when you want to, for example, compare multidimensional time series. So in that sense, one of the ways in which you can go is via signatures and then trying to measure distances between.
Okay.
Yes.
Using signatures. So you mean that you compute the signature and then you measure the distance between the signatures?
Between the signatures, yes. But then obviously in time series there are the issues that, I mean, if you take, let's say, a very simple autoregressive process of order 1, okay, very basic. If you take just the process itself, then the signature is not able to give you any information in distinguishing two different autoregressive processes of that type. But then what you can do, you can augment the process by taking a lead process on top of that and transformations, and then you apply the signature. But my view is very clear. I mean, that's
Typically, if you want to capture something on the trajectory, you always need a second one. Because otherwise you essentially get powers, no?
yeah.
And then you do not have any information on what happened before.
Yes.
Yeah.
Sure. Want to add again? That supposing I know the structure of the process that I'm approximating, and can I tell from the moment, say, as to whether it will be recommended that I go to level 3 or 4 or stop at, well, like people think that, okay, skewness is important, skewness is being prized, kurtosis is an issue. And so if I find a density in which the skewness is 0 and the kurtosis is 3 or something, then I say, okay, you stop at level 2. Can we get a recommendation of what level one should go to in terms of the moments?
Yes, I would say. You mean knowing the moments of the process?
Yeah. To where should I stop in my signatures?
So I think that for this, it makes sense to first think about what you would like to use your signature for. So.
Well, to price an option.
Okay, I mean that probably depending on the shape of your payoff, okay? It can be that
we know that it's the hockey stick with the option payoff at the end.
Okay, so what I meant is that
it's not differentiable, but we know what it is.
Yes, but I think that depending on that, you can try to see what is the error, and you can also compute the error exactly, okay?
I see.
And so maybe from... depending on the payoff, you can have different terms. So I guess that if you have an option that is that relates on the tails, for example, then maybe you need to go a bit deeper, no? Yeah. To be able to capture it. But if you have an option where most of the thing is not on the tail, then maybe you don't need it.
Yeah, well, I mean, if the strike is out there, then...
Exactly, this is exactly what I mean.
Okay, right.
Heuristically, I think that maybe, I mean, if you're interested in, you could say that if you're interested up to the variance, then probably you have to go to the fourth moment so that you have a variability for the Russell.
If you're interested in the variance, maybe the second one.
Yeah, but the point then you go to the fourth, then you have the variability for the variance.
Okay, yeah.
So that if you want to get the confidence intervals for the variance.
Yeah.
Makes sense. So heuristically, I think, would be a way.
Yeah.
So we noticed that, like for shorter, if you want to get at the same time shorter and longer maturity, where with shorter I mean, if I remember right, we take like 2 weeks. Then we were going till level 3 or 4. And then if you want to use the exactly same coefficients. Otherwise, if you split and you say, okay, it's okay for me to have different coefficients for shorter and for longer, like a time-dependent type of coefficient, then you can also stop much earlier.
Aye.
And the difficult things are, of course, the far out and in the money strikes for
Right.
very short maturity. This years that comes out.
Okay.